All right, welcome to the Advanced Concepts section of Module 3, Design, Integration, and Cost. So here's where we are. You've already built a solid foundation. You know the frameworks, the contracts, and the basic rules. That's great. But now we're going to take all of that and crank up the complexity, because that's exactly what NCARB does on the actual exam. They don't just ask you to define a term, they give you a scenario with competing priorities and ask you to pick the best move. We've got 16 slides ahead of us, broken into 5 sections, and each one is designed to push your thinking from "I know the concept" to "I can apply it under pressure." So let's preview what's coming. Section 4.1 tackles advanced cost, LCCA, total cost of ownership, reconciling estimates. Section 4.2 tackles advanced V, fast diagrams, VE and delivery methods, quality/cost/schedule. Section 4.3 tackles systems integration, structural architectural, MEP allocation, envelope structure, vertical transport. Section 4.4 tackles advanced specs, performance specs, substitutions, spec drawing coordination. Section 4.5 tackles design review, peer review, document coordination, managing changes. Here's the thing about these topics. This is where most candidates lose points on the exam. Not because the material is inherently harder, but because the questions require judgment, not just recall. You can't memorize your way through these. You've got to think through scenarios, weigh competing interests, and pick the best answer when multiple options seem reasonable. So let's start building that skill right now. Life cycle cost analysis evaluates the total cost of ownership over a building's useful life, not just the initial construction cost. LCCA is essential for comparing alternatives that have different initial costs but different long-term operating and maintenance profiles. The architect who only compares first costs is the architect who recommends the wrong system and loses the client's trust when the operating bills arrive. This list provides common ROI examples for sustainable building features. High-efficiency HVAC achieves payback in 3 to 7 years from energy savings. Daylighting with automated controls pays back in 5 to 10 years, plus delivers productivity gains. Green roofs take 15 to 20 years, but stormwater credits can shorten this. Solar PV pays back in 7 to 12 years, depending on utility rates and incentives. Low-flow fixtures pay back in just 1 to 3 years and are almost always cost-effective. These timeframes help prioritize sustainable investments. The HVAC decision, a worked example. This list describes the 6-step budget reconciliation process when cost estimates exceed the owner's budget. First, verify the estimate by checking quantities, unit costs, and assumptions. Second, identify the gap. How much over budget and in which systems? Third, evaluate VE options that maintain function at lower cost. Fourth, prioritize with the owner to decide which VE items to accept. Fifth, adjust scope if needed through deferred work, phasing, or reduced program. Sixth, document every decision and its rationale. This systematic approach prevents reactive cost cutting. The expensive system costs $280,000 more upfront, but saves $440,000 over 30 years. An architect who presents only first cost loses the argument to the contractor saying, "Go with the cheaper one." An architect who presents the LCCA wins the client's confidence and often wins the project. The discount rate sensitivity. LCCA results depend heavily on the discount rate chosen. A higher discount rate makes future savings look less valuable, favoring lower first costs. A lower discount rate makes long-term savings look more attractive. Always document the discount rate assumption. Changing from 3% to 7% can flip the recommended choice. Here's the key insight. LCCA uses present value analysis to compare alternatives. A higher first cost may have lower life cycle cost. The exam tests whether candidates can identify that lowest first cost does not equal lowest total cost, and whether they can present the numbers in a way that lets the owner make an informed decision. Total cost of ownership extends LCCA to include indirect costs like productivity impacts, user satisfaction, and environmental externalities. Return on investment (ROI) calculations help owners justify higher first costs for sustainable or high-performance features. This table outlines the key AIA B101 provisions governing budget and cost responsibility. The architect must design to the owner's budget. The budget is a design constraint, not just a target. If the project is over budget, the architect revises documents at no additional cost, unless the overage was caused by owner scope changes. The owner has the option to increase the budget, but is not obligated. The owner can reduce scope or authorize rebidding to seek better market pricing. Understanding these provisions is essential for exam questions about architect-owner responsibilities. This table explains fast diagram concepts used in formal VE studies. Higher-order functions represent the why, the purpose being served, like protecting occupants. Basic functions are the primary functions being analyzed, like enclosing space. Required secondary functions support the basic function, like resisting weather or controlling heat flow. Design objectives are desired but not essential functions, like enhancing aesthetics. The how-why logic chain links these functions. Reading left answers how and reading right answers why. A critical warning. Simple payback is the most commonly misused metric. It ignores the time value of money and what happens after payback. A 10-year payback on a 30-year system is excellent, but simple payback makes it look unattractive. Here's the key insight. The exam rule. When comparing options with different first costs and operating costs, use NPV or SIR. Never simple payback alone. Simple payback is a screening tool. NPV is the decision tool. A 10-year payback on a 30-year roof, 20 years of free savings after year 10, beats a 5-year payback on a 7-year compressor, only 2 years of free savings. The length of life matters as much as the payback speed. When cost estimates exceed the owner's budget, the architect must lead the reconciliation process. This is one of the most politically sensitive aspects of practice and a frequent exam topic. This list walks through the 6 steps of creating a fast diagram. Define the scope of the study to focus on a specific building system or component. Identify all functions using verb-noun pairs like enclosed space or support load. Classify each function as basic, required secondary, or design objective. Arrange functions in how-why logic chains reading left to right. Identify the highest cost functions. These become VE targets. Brainstorm alternative ways to achieve those high-cost functions at lower cost while preserving the intended outcome. This table shows how VE works differently across 4 delivery methods. In design, bid, build, VE occurs only during design with no contractor input. Post-bid VE becomes a change order. CM at risk provides the most effective VE because the CM gives continuous, real-time cost feedback during design. Design build integrates VE internally within the design build team, trading design decisions against construction efficiency. IPD creates the highest VE motivation because all parties share savings through collaborative incentives. Here's the key insight. Under AIA B101, if the lowest bona fide bid exceeds the owner's budget, the architect must modify documents at no additional cost unless the overage is caused by scope changes the owner directed. This is a critical exam distinction. FAST, Function Analysis System Technique, diagrams are a core VE tool that maps relationships between functions using how-why logic. Reading left to right answers how. Reading right to left answers why. This forces the team to understand what each building component actually does. This list covers Value Engineering Change Proposals, VECPs, which occurred during construction. The contractor proposes alternatives and savings are typically shared between owner and contractor, often on a 50-50 basis. The architect must review every VECP for compliance with design intent, code requirements, and performance standards. VECPs cannot reduce the functional requirements of the contract. Federal projects often require VECP provisions in their contracts. The critical distinction: a VECP is not a substitution. Substitutions replace products, while VECPs change the design approach while maintaining function. This table illustrates how 5 VE decisions affect the triple constraint of cost, schedule, and quality. Switching steel to precast may save 10 to 15% on structure and could be faster to erect, but changes the aesthetic and connection details. Reducing floor-to-floor height saves on cladding and risers and speeds construction, but reduces ceiling height and MEP flexibility. Combining mechanical rooms eliminates equipment duplication, but creates longer duct runs. Standard curtain wall costs 30 to 50% less than custom, with shorter lead times. Deleting a basement saves major excavation costs, but requires relocating that program space. Here's the key insight. Fast diagrams prevent solutioneering, jumping to solutions before understanding the problem. By mapping functions first, the VE team can identify where cost is disproportionate to function value. The project delivery method significantly affects when and how value engineering occurs. Each delivery method provides different VE opportunities and constraints. This table addresses 5 common structural architectural grid coordination issues. Economical column spacing of 25 to 35 feet for steel or 20 to 30 feet for concrete must align with room sizes and corridor widths. Column sizes increase at lower floors, but should be coordinated with wall thickness to minimize intrusion. Transfer conditions are expensive and should be avoided unless essential. Floor-to-floor height must balance deeper beams that span farther against maximum ceiling height requirements. Lateral system elements like shear walls should be located at stairs, elevators, and party walls to minimize their impact on the floor plan. This table provides MEP space allocation rules of thumb that architects must incorporate during early design. Main mechanical rooms require 3 to 8% of gross floor area with 12 to 16 feet clear height and access for equipment replacement. Electrical rooms need 200 to 400 square feet per floor, with NEC required 36-inch minimum clearance in front of panels. Telecom rooms need 150 to 300 square feet per floor, stacked vertically. Ceiling plenums require 18 to 36 inches. Vertical chases consume 2 to 4% of floor area. Plumbing walls need 6 to 8 inches minimum, with wet rooms stacked vertically. A critical warning: a VECP is not a substitution. Substitutions replace specified products with alternatives. VECPs change the design approach while maintaining function. The architect must approve both, but the review criteria are different. Every VE decision affects 3 interrelated constraints: quality scope, cost, and schedule. Changing one always impacts at least one other. The architect must help the owner understand these trade-offs. This list covers 5 envelope integration principles. The air barrier, vapor retarder, and thermal insulation must all be continuous across the entire building enclosure. Any structure penetrating the insulation plane creates thermal bridges that degrade performance. Shelf angles supporting masonry must accommodate structural deflection, typically limited to span divided by 600. Window and curtain wall anchors must be coordinated with the structural frame for proper load transfer. Expansion joints in cladding must align with structural expansion joints, and flashing and drainage must be detailed at every floor line and opening. Here's the key insight. The best VE solutions improve 2 of 3 constraints without significantly harming the third. The exam rewards candidates who can identify VE strategies that save cost and time without sacrificing function. The structural grid is one of the most consequential early decisions in building design. It establishes column locations that affect room sizes, corridor widths, parking layouts, and facade rhythms. Grid coordination between structural and architectural requirements must be resolved in DD. This list details 6 elevator integration requirements that affect architectural design. Machine room-less elevators still require overhead space and pit depth, even without a separate machine room. Elevator lobbies may be required for fire service access, depending on the code. Shaft walls are typically 2-hour fire-rated construction. Venting requirements vary between pressurized and vented shaft approaches. Structural loads from elevator equipment require early coordination with the structural engineer. ADA and ICC A917.1 requirements dictate minimum cab sizes and door widths. Here's the key insight. A 30-foot bay works for many building types. Offices, 5 workstations at 6 feet. Parking, 3 spaces at 8.5 feet and drive aisle. Residential, 2 units at 15 feet. Choosing a universal bay size that serves multiple floor uses reduces structural cost dramatically. MEP systems consume 15 to 25% of a building's gross area and a significant portion of the floor-to-floor height. Inadequate space allocation for MEP is one of the most common coordination failures and a leading cause of change orders. This table shows 6 performance criteria that should be specified in performance specifications with their verification methods. Thermal performance specifies U value, SHGC, or R value and is verified through ASTM tests or thermal modeling. Structural capacity specifies load ratings and deflection limits verified through calculations or load testing. Acoustic performance specifies STC, IIC, or NRC ratings verified through ASTM testing. Air infiltration, water penetration, and fire resistance each have specific ASTM or UL test standards for verification. A critical warning: the most expensive sentence in construction. There is not enough room in the ceiling for the ductwork. This means either the floor-to-floor height increases, structural redesign, or the ductwork route changes, MEP redesign. Both are costly in DD, catastrophic if discovered in CDs. The interface between the building envelope and the structural frame is one of the most technically demanding areas of building design. This is where thermal bridging, moisture management, air barriers, and structural connections all converge. The exam tests this heavily because failures at the envelope structure interface produce the most expensive construction defects in commercial buildings. This list provides 6 keys to writing effective performance specifications. Define measurable, testable criteria and avoid vague language. Specify test methods and acceptance standards explicitly. Include the environmental conditions under which performance is measured. Require submittals demonstrating compliance before fabrication begins. Include mock-up and field testing requirements for critical assemblies. Define remediation procedures if performance criteria are not met, so there is a clear path forward when issues arise during construction. This table shows 4 substitution types with their timing and approval process. Pre-bid substitutions before the bid date are communicated to all bidders via addendum if approved. Post-bid or pre-award substitutions after the bid but before the contract require careful review because they may affect bid evaluation. Construction substitutions after contract award require formal submittals and architect review. VECP substitutions during construction require cost analysis and a shared savings agreement between owner and contractor. Here's the key insight. Thermal bridging is often underestimated in energy calculations. A steel stud wall with continuous insulation can lose 40% more heat than the R value alone suggests because of thermal bridges at framing members. ASHRAE 90.1 and IECC both require continuous insulation specifically to address this, and the exam tests whether candidates can recognize when thermal bridging is hurting building performance. Vertical transportation and fire protection systems have rigid code requirements that significantly influence the architectural plan. These systems must be integrated during DD because relocating them later requires extensive redesign. This list covers product representation and warranty concepts. Manufacturers provide product data, test reports, and samples for architect review. Shop drawings are the contractor's interpretation of the design. The architect reviews them for conformance with design intent. The standard general warranty is 1 year per AIA A201. Extended warranties for roofing, waterproofing, and windows are specified separately by the architect. Warranty start date is typically substantial completion, not the installation date. Manufacturer warranties cover the product, while contractor warranties cover the installation quality. This table identifies 4 common drawing specification conflicts with prevention strategies. Different product names on drawings versus specs are prevented by using keynotes referencing spec sections instead of product names on drawings. Quantity conflicts between plans and specs are prevented by having drawings show quantity and specs describe quality without duplicating. Detail conflicts between sections and specs are caught by cross-referencing during QC review. Scope gaps, where neither document addresses a transition detail, are prevented by using a responsibility matrix to assign every scope element. Here's the key insight. Fire protection is not an add-on, it is an integrated building system. Sprinkler head locations affect ceiling design, smoke barriers affect plan layout, and stair pressurization affects HVAC design. Integrate fire protection in DD, not as an afterthought in CDs. Performance specifications define what results are required without dictating how to achieve them. They transfer performance risk to the contractor or manufacturer, but require the specifier to clearly define measurable criteria and acceptance testing methods. This list provides 5 coordination best practices for preventing drawing specification conflicts. Use keynotes on drawings that reference master format section numbers to maintain the link between visual and written documents. Maintain a drawing specification cross-reference log throughout the project. Never put product names or model numbers on drawings. They belong exclusively in specifications. Review specifications and drawings simultaneously during quality control rather than independently. Use NIC designations carefully because they can create unintended scope gaps. This table distinguishes 4 types of design review by who performs them, when they occur, and what they focus on. Internal QC reviews by senior staff at milestones focus on drawing accuracy and coordination. Independent peer reviews by outside architects or engineers at end of DD or mid-CD focus on code compliance and constructability. Owner's independent reviews by the owner's consultant at each phase submission focus on budget and program compliance. Agency code reviews by the building department during permit submission focus strictly on code compliance and life safety. Substitution management is a critical specification coordination task. The specification must clearly define when substitutions are permitted, what documentation is required, and who bears the cost of evaluating alternatives. This list covers 7 topics that should appear on every effective design review checklist. Code compliance, including occupancy, construction type, egress, and accessibility. Structural architectural coordination for grid alignment and clearances. MEP architectural coordination for equipment rooms, plenum space, and access panels. building envelope integrity, including air barrier continuity, thermal bridging, and moisture management, life safety coverage for sprinklers, fire-rated assemblies, and smoke barriers, specification drawing consistency through cross-referencing key details, sustainability compliance for energy codes and lead credit documentation. This table identifies 5 common coordination errors between disciplines. Architectural and structural drawings showing columns at different locations are prevented by sharing a BIM model with a linked structural grid. Ceiling height conflicts with duct routing are prevented by establishing plenum depth early and running clash detection. Electrical panel locations conflicting with the architectural layout are prevented by coordinating electrical room sizes during DD. Structural penetrations for MEP not coordinated are caught by requiring MEP to locate penetrations on structural drawings. Building floor elevation not matching site grading is verified by checking finished floor elevation against the civil grading plan. Here's the key insight. The architect does not approve shop drawings. The architect reviews them for conformance with the design intent. Approved implies liability for the contractor's means and methods. The correct stamp language is reviewed or no exceptions taken. Specification drawing coordination is one of the most error-prone areas of construction documentation. Conflicts between drawings and specs generate RFIs, change orders, and disputes. A systematic coordination process during DD and CD phases is essential. This table shows 5 types of design changes, who initiates them, and how the architect should respond. Owner-directed changes require documentation and assessment of cost and schedule impact, with a request for additional services fees. Code-driven changes from officials are implemented as basic services if within original scope. Coordination changes resolved between consultants carry no additional fee under normal circumstances. Market-driven changes, when estimates exceed budget, may require redesign at the architect's cost under AIA B101. Scope creep from gradual small additions must be tracked and documented with additional services requests when the cumulative impact becomes significant. This list provides 6 design phase risk management practices. Maintain a design decisions log, recording who decided what and when. Get written approval at each phase transition from SD to DD and DD to CD. Use a formal change management process even during design phases, not just during construction. Track consultant hours against fee to identify scope creep early. Include additional services provisions in sub-consultant agreements. Review insurance coverage annually to ensure it matches current project risks. The single most important tool is documentation. Verbal agreements without written records leave the architect unprotected. A critical warning. Under AIA A201, drawings and specifications are complementary. If something is required by either, it is required. But when there is a direct conflict, most contracts give precedence to specifications over drawings. However, this varies by contract. Always check. Peer review involves an independent, qualified professional examining the design documents for errors, omissions, code compliance, and design adequacy. It is different from internal QC. Peer reviewers bring fresh perspective and are not invested in the design decisions. This table distinguishes 4 types of design review by who performs them and what they focus on. Internal QC reviews by senior staff at milestones focus on drawing accuracy and coordination. Independent peer reviews by outside professionals at end of DD focus on code compliance and constructability. Owners' independent reviews focus on budget and program compliance. Agency code reviews by the building department focus on code compliance and life safety. This list covers 7 topics for effective design review checklists. Code compliance, including occupancy, construction type, egress, and accessibility. Structural architectural coordination for grid alignment and clearances. MEP architectural coordination for equipment rooms and plenum space. Building envelope integrity, including air barrier continuity and thermal bridging. Life safety coverage for sprinklers and fire-rated assemblies. Specification drawing consistency. Sustainability compliance for energy codes and lead documentation. A typical commercial project may have 8 to 12 consultants producing documents simultaneously. The architect is responsible for coordinating these documents into a coherent set. Coordination failures are the leading cause of RFIs and change orders. This table identifies 5 common coordination errors between disciplines with prevention strategies. Column location discrepancies between architectural and structural drawings are prevented by a shared BIM model. Ceiling height conflicts with duct routing are prevented by establishing plenum depth early. Electrical panel conflicts are prevented by coordinating room sizes during DD. MEP penetrations through structure require early coordination. Floor elevation mismatches with site grading must be verified against the civil plan. Here's the key insight. BIM, Building Information Modeling, does not eliminate coordination errors. It makes them visible earlier. The architect must still lead coordination meetings, assign action items, and verify resolutions. BIM is a tool, not a substitute for professional judgment. Scope creep. The gradual expansion of project scope without corresponding budget or schedule adjustments is one of the greatest risks to project success. The architect must manage scope actively, documenting every change and its impact. This table shows 5 types of design changes and how the architect should respond. Owner-directed changes require documentation and cost schedule impact assessment with additional services fees. Code-driven changes are implemented as basic services within original scope. Coordination changes between consultants carry no additional fee normally. Market-driven changes when estimates exceed budget may require redesign at the architect's cost per AIA B101. Scope creep must be tracked and documented with additional services requests when cumulative impact is significant. This list provides 6 design phase risk management practices. Maintain a design decisions log, recording who decided what and when. Get written approval at each phase transition. Use a formal change management process even during design phases. Track consultant hours against fee to identify scope creep early. Include additional services provisions in sub-consultant agreements. Review insurance coverage annually. The single most important tool is documentation. Verbal agreements without written records leave the architect unprotected. A critical warning. The single most important risk management tool is documentation. If the owner verbally approves a scope change and later denies it, the architect who documented the conversation in writing is protected. The architect who relied on verbal approval is not. Let's bring it all together. You've just worked through the entire advanced layer of project planning and design module 3, design, integration, and cost. That's a lot of material, so let's recap what you've learned and why it matters. Section 4.1, Life Cycle Cost. LCCA captures operations and maintenance. First cost alone is a misleading metric for owner decisions. Section 4.2, Advanced VE. Fast diagrams map function relationships. VE under CM at risk happens earlier and more collaboratively. Section 4.3, Systems Integration. Structure and envelope must coordinate for thermal performance. MEP space allocation drives floor-to-floor height. Section 4.4, Performance Specs. Performance specs define outcomes, not products. Substitution requests require proof of equivalence. Section 4.5, Design Review. Peer review catches errors before they become change orders. Scope changes after DD require formal authorization. Section 4.5, Change Management. Document every design change with cost and schedule impact. Undocumented changes become claims. The thread connecting all of these sections is this: project planning and design isn't about creativity alone. It's about integrating codes, systems, costs, and coordination into a design that actually works. Get this right, and your documents hold up under construction. Your next step is the Advanced Check Quiz. These questions are harder. They test application, not just recall. Take your time, read each option carefully, and use the explanations to refine your thinking. When you finish this, you'll have completed the full Module 3 content. You've built a solid foundation. Time to put it to the test.